Hello and welcome. In this video, we're going to be taking a look at a couple topics that are really just a follow-up from a previous video on partial derivatives. We'll start off by taking a look at where a relationship between multiple variables may not be expressed as a function. Maybe it can only be expressed in the form of some sort of equation. Well, if we want to figure out how one quantity varies with respect to one of the other quantities in that equation, we're still looking for a partial derivative, but we have to compute it through implicit differentiation. And that's a pretty big topic. It comes up fairly often, and we'll see actually in future videos after this that there are multiple methods for being able to compute partial derivatives in an implicit relationship like that. And we'll just start to scratch the surface of the world of partial differential equations in this video as well. Let's start with implicit differentiation. In this case, implicit differentiation is going to be a very similar method to what we use in single variable calculus. Let's take a look at an example. We're typically going to have a relationship between three or more variables here in the form of an equation. In this case, we have an equation relating x, y, and z. Since we have three variables, this could be represented as a surface in 3 dimensions. And I won't tell you exactly what that surface looks like right now, but we'll take a look at it a little bit later in Maple. Let's suppose we want to see how z varies with respect to x and y at some point on the surface. And you can go ahead and check and make sure that this point does in fact exist on the surface. X equals 4, y equals 0, and z equals 1. If you plug those values in on the left-hand side of the equation, you should get 2, which satisfies the right-hand side of this equation. Now, if we're looking for the partial derivative of z with respect to x, as we saw in a previous video, we're going to essentially just treat y as constant. But we have to take the derivative of both expressions on the left and right-hand sides of this equation. And every time that we see that we're taking the derivative of some expression involving z, we are treating z as dependent on x. So essentially, we're applying the kind of chain rule that we're used to from single variable calculus. The first thing we'll do is we'll take the left-hand side of this equation, and we will apply the partial differentiation operator, del by del x. And we'll do the same thing to the right-hand side of the equation, and of course, that's going to be the easier side. Over there, we simply have 2. That's a constant, and the derivative of a constant with respect to any variable is going to always be equal to 0. Over on the left-hand side here, though, we're going to have to be a little bit more careful. What we're treating as a constant at the moment is simply just y. X is going to be what we're taking the derivative with respect to, so it's pretty straightforward. Every time we see functions of x, then we're going to be thinking about classic rules like power rule, chain rule, exponential rule, etc. When we see functions of z, we're going to have all of those same rules, except we have to also remember that z is dependent on x. We have a lot of chain rules to worry about. We have some expression inside the parentheses here, all squared. So we can start with the derivative of all of that green expression squared, and that derivative would be 2 times that expression to the power 1. And now we need to take a look at the derivative of the inside. So we'll go ahead and multiply by the derivative of 3 minus square root of x squared plus y squared. Well, 3 is simply a constant, and we only need to worry about the second term here. And we're going to need another chain rule. At this point in time, we have x squared plus y squared as the inside function inside of the negative root. So let's start off with what the derivative of the negative root of some expression is. And using the power rule, that would simply be negative 1 over 2 times the root of that expression. Now that expression is still x squared plus y squared, and we need to multiply by the derivative of that expression. X squared plus y squared is a fairly straightforward expression now to take a look at, since the derivative of x squared is simply just 2x, and the derivative of y squared is 0. We don't really have to write that 0. We could just leave that as 2x. So there's a double chain rule. We have a green expression inside of the blue parentheses all squared, and we have x squared plus y squared as an expression inside the root. 2 chain rules for that first term. And now we get to plus z squared. And you can think about this as really being a chain rule. The derivative of some quantity squared would be 2 times that quantity. However, since z depends on x, we need to multiply by the partial derivative of z with respect to x. Now, at this point in time, you can see we have quite a mess of different factors all put together, and we have 2 different terms. The ultimate goal here is to be able to solve for the partial derivative of z with respect to x. At this point, we can use algebra to solve for del z by del x. And keep in mind that if z appears in more than one place in this equation, you could have multiple del z by del x's throughout the equation. You'd have to put them all on one side and factor that del z by del x out so that you can solve for it. We're kind of lucky in this case that we only see del z by del x in one term, which makes it kind of like a very easy linear equation to solve for del z by del x in this case. We're going to take this massive mess of terms over here and we're going to move it to the other side. But before we do that, we can see we have a nice factor of 2 that can cancel out from both of these first 2 factors there. Tidy things up here a little bit, we have the factor in parentheses, we have a factor of -1 and a factor of 2x all multiplied together across the numerator, and then in the denominator we simply just have the square root of x squared plus y squared. This whole term, since it's negative, will just get added to the other side. And now we can see we've got all of the terms involving del z by del x on one side of the equation, and we can simply divide both sides of the equation by 2z. Before we do that, why don't we cancel 2's on both sides? Now we can simply divide by z to get the partial derivative of z with respect to x equal to x times 3 minus root x squared plus y squared all over z times root x squared plus y squared. Now remember, this is the partial derivative of z with respect to x at any given point x, y, z. In order to actually evaluate this at a point, you may notice that we actually have to plug in x, y, and z into this. This partial derivative is actually expressed in terms of all 3 values, so you do need to plug in the corresponding z value in this case. As far as a notation for plugging in that point, we might decide to use a vertical bar here. Del z by del x evaluated at a point 4, 0, 1. In this case, since we have our 3 variables x, y, z, it's pretty obvious that x, y, z are in that order, in this ordered triplet. But if it's not obvious, we can always specify by having x, comma, y, comma, z equal to 4, comma, 0, comma, 1 down there in the subscript. I'm going to omit that for now since we typically have ordered triples of the form x, y, z already. It's at this point in time that we can go ahead and plug in x equals 4, y equals 0, and z equals 1 into this equation. If we evaluate that expression, we have 4 times 3 minus 4. That gives us -4 in the numerator, and then we have 4 in the denominator. And overall, that gives us a partial derivative equal to -1. This is the rate of change of z with respect to x at that specific point. Now, question here actually also asks us to calculate the partial derivative of z with respect to y at that same point. And we're very lucky here because you can see just how sort of symmetrical this equation looks. Whether we're taking the partial derivative with respect to x or with respect to y, we should probably get a very similar answer. But just remember that when we are looking for the partial derivative of z with respect to y, we are going to treat x as constant, and we're going to be treating z as dependent on y. And anytime that we see z, we're going to have to apply the sort of chain rule that we're used to from single variable calculus. You can go ahead and try this on your own, and you should end up getting a very, very similar expression. Del z by del y will equal this time y times 3 minus root x squared plus y squared all over z times root x squared plus y squared. You can see the difference there is y, because in that little purple expression there, we are treating x as a constant and y as our variable this time. The derivative of x squared would be 0, and the derivative of y squared would be 2y. So it's really only a very small factor that changes depending on if we are differentiating with respect to x or y. This time, plugging in 4, 0, 1, since y is equal to 0, we get 0 in the numerator. And that means that our partial derivative of z with respect to y is equal to 0. Now, you might be thinking, if you go back to single variable calculus, that that is the slope of a horizontal line. That's essentially what's going on here. There is kind of a horizontal line comparison, but we're going to need Maple in order to sort of visualize that. We've got with plot so that we can use three-dimensional plotting tools. And let's define this equation, EQN for short, as the equation that I was just taking a look at. And I didn't tell you what that shape was, but I'm going to spoil it right away and tell you that that's a torus. Essentially, that's a donut. Now, there are other forms of equations for a torus. Using Cartesian coordinates, x, y, and z might not give us exactly the nicest looking graph, but it does define this surface of a donut. Let's define that equation first. And why don't we take a look at how we compute derivatives implicitly in Maple? It's actually just using the implicit diff command, which is what we're usually using in single variable calculus. It's exactly the same command. We give it an equation that we're trying to differentiate, and then we have to specify that we want z as a function of x. This is going to compute del z by del x. And then I'm also going to go ahead and plug in x equals 4, y equals 0, z equals 1 into that little percentage sign shortcut and simplify the result. You can see we do in fact get -1, which is what we computed by hand. We can do the same thing for del z by del y. We just need z with respect to y in the implicit diff command. And again, we'll plug in the point and we end up getting 0. Now, I'm going to have to put a lot of plots together here to explain what that -1 and 0 represent. We're going to use implicit plot 3D on the equation of the torus. That's going to give us a donut. And then we're going to be taking a look at two planes, the plane x equals 4 and the plane y equals 0. I'm going to put the point on the torus, 4, 0, 1, as well as the two sort of tangent lines that I was alluding to. So let's go ahead and put them all together. Here is that torus. Now, it's not exactly to scale. I can go ahead and click the 1-to-1 button to get a better sense of that donut. And there it is. The origin's right there in the middle where y is equal to 0, x is equal to 0, and z is equal to 0. That's somewhere right in the center. And you can go ahead and take a look at the blue and red planes. If we're looking for the partial derivative of z with respect to x, that means we're keeping y constant. Y equals 0, in fact, is this blue plane, and we can go ahead and take a look at the donut from the perspective of that blue plane. Just a little cross section. And I've oriented it this way so you can see x is increasing. And this blue line is a tangent line to the circular cross section of the donut. Now that circular cross section actually has multiple z values. It's not a function. We couldn't represent this torus in the form of z equals a function of x and y. That's why it's so important to know implicit differentiation and why we have to plug in a specific z coordinate corresponding to that point up there, not the point down there where we also have x equals 4 and y equals 0. And you can see it's actually to scale. That blue line does look like it has a slope of -1. The equation of that line would be 4 plus t, comma 0, comma 1 minus t. It's a line passing through the point 4, 0, 1, and I've made sure that as x increases by 1, that z is decreasing by 1. Now let's go ahead and take a look at the partial derivative of z with respect to y. That's where we hold x constant and x equals 4. And you can see, looking at this from the perspective of that red plane and having y increasing along the bottom axis, z increasing along the vertical axis, we get a nice little slice. It's actually an ellipse in this case. And at that green point, you can see we have a horizontal tangent line. And that's a pretty easy line to also make. That would simply just be 4, comma 0 plus t, comma 1. It means that x and z are never changing, and this line only goes back and forth parallel to the y-axis. And there you can see what we're really doing with partial derivatives. Now, as a little spoiler for future topics and future videos, you can just maybe imagine if you take that red line and that blue line, you can form a plane. And that plane would actually be tangent to the surface of the torus. So rather than just thinking about these two tangent lines from cross sections of the torus, what we can do with this and where we can go with this is we can actually take a look at tangent planes to surfaces. But like I say, we'll hold on to that for now and we'll take a look at that in a future video. There's one other topic that we can take a look at in this video that is also related to partial derivatives, and that is a partial differential equation. Partial differential equation, as you may be able to guess from the name, is an equation that involves partial derivatives. If you want to be a little more descriptive than that, these are equations that consist of some quantity, maybe it's z, that is dependent on multiple variables, maybe they're x and y. And this equation not only involves that z, but it also involves the partial derivatives of that quantity z. Now, it doesn't have to be, of course, just z, x, and y, although that's what we seem to be using most often. But let's take a look at maybe a different example that doesn't just use our standard x, y, and z. Let's take a look at a famous example called the heat equation. And for simplicity, let's take a look at the one-dimensional heat equation. Now, for the one-dimensional heat equation, what we're going to do is we're going to imagine a very thin rod, maybe just consisting of something like metal. Now, for simplicity, we're going to have this rod be parallel to, let's say, the x-axis. One end of the rod is going to be at a position of x equals 0, and the other end of the rod is going to be at a position of x equals L. What we're going to do right off the bat is we're going to add a little bit of heat wherever we want along the length of this rod. So let's just indicate that as maybe we have one sort of hot spot here in the middle, maybe because we've just held a candle underneath this rod for a short period of time. Now, of course, this rod isn't necessarily just floating in space. It has to probably be held there while we're heating up the rod, but we're going to assume that both ends of the rod are insulated. There's no way that heat can escape. And what we're going to define is a function of two variables. That function is going to represent temperature at a specific point. At any given x value, we have a certain temperature. But the moment that we stop heating up this rod and we let heat do its thing, you can imagine that that temperature is not going to be constant, even at a fixed point. And so temperature is also a function of time. We have a function temperature at any point x along the rod, where x is from 0 to L, and at a time t, where we're going to typically start at t equals 0 and let t go off to infinity. You can probably imagine what's going to happen to temperature. If we are no longer going to be adding any heat to this system, then the heat that we currently have is going to diffuse through the rod. Cooler ends of the rod are going to heat up as heat distributes across the rod. And maybe you can imagine that if we let T go to infinity, we should have a nicely evenly distributed heat, or in this case, evenly distributed temperature across the rod. Let's take a look at the differential equation that governs how the temperature at any point and time along the rod is going to change. The heat equation says the rate of change of temperature at a point x and time t with respect to time is equal to some constant alpha times the second derivative of the temperature at some point in time with respect to x squared. Now, remember, U is temperature, and that's the temperature at a specific point and a specific time. On the left-hand side here, we have a first derivative. On the left-hand side, we are differentiating with respect to time. So this is the rate of change of temperature, maybe in degrees, per unit of time. So per second. Temperature per second. That's talking about how temperature is just changing as time increases. On the right-hand side, we have a spatial derivative. We're talking about how temperature is changing with respect to position. This is the second derivative of temperature with respect to x twice. So as we're changing x to the right or changing x left, it's almost like a little bit of concavity, although it's kind of hard to visualize it that way. It's really related to how heat is diffusing. In fact, that alpha there is actually known as the thermal diffusivity constant. That constant depends on a few things, such as specific heat capacity of that material, depends on the density of that material, as well as thermal conductivity. Some materials just conduct heat better, in which case the rate of change of temperature can be greater with respect to time. And the solution to this particular heat equation might be a little bit tough to derive right now, but you might be able to imagine what a solution could look like. Now, what's interesting about differential equations, whether they're ordinary or they're partial differential equations, ODEs or PDEs, is that the solution to them is actually a function. So we're actually trying to come up with a function for temperature in terms of x and t that satisfies this relationship. If we knew what the solution was, we could plug it in. We could just see that the left-hand side is equal to the right-hand side. Now, that's a lot of work. We're not going to get to that in this video. You're going to have to go ahead and dive into the world of partial differential equations and figure out how to solve these kinds of equations for yourself. But you might be able to imagine what the solution could look like. We could actually try to graph that function. Since the function is u for temperature in terms of a point x and time t, we can actually take a look at what that would look like when t equals 0. If we wanted to look at the graph of that function, at least just when t equals 0, we could just have this be really like a two-dimensional curve where we have u on the vertical and we have x on the horizontal. And we'd have a hot spot somewhere in the middle corresponding to the hot spot where we've added all the heat. This is just the initial time of the solution. Now, what if we were to go ahead and let t get larger now? Let's suppose we want to take a look at the solution to this equation, but maybe we want to let t go all the way up to 50 seconds now. You can probably imagine what the solution would look like much, much later. In this case, the distribution of heat is a little bit more uniform. Cooler ends of the rod have heated up a little bit, and the hottest part of the rod has cooled down a little bit. And this is just two snapshots of what that solution would look like. The actual solution would be something of the form u of x comma t equals an expression involving x's and t's. And then we could simply plug in any value of x we want and any value of t we want and figure out the temperature at that point and time. But like I say, that's a little bit beyond the scope of this video. Hopefully for now, at least you can get a good sense of what the usefulness of partial derivatives can be. If we maybe don't have a function, but we have an equation that relates as many variables as we want, well, we can use implicit partial differentiation in order to express the rate of change of one quantity with respect to another, while keeping all of the other ones treated as constants. And we just kind of scratched the surface of the world of PDEs, which is quite a more intense area of calculus with lots of new strategies for how you solve those kinds of equations. So maybe you can get into that a little bit later. Thanks for watching, and I'll see you in the next video.